in this class, we'll talk about the artificial variable technique. So far as we learned for simplex method, it is a very useful way for solving linear programming problems. However, we say to start the simplex method, we need to put our LP problem in the standard form, meaning we want to maximize an objective function. So if we have a minimization problem, we change the objective function to maximizing -z. On the other hand, all the constraints in the standard simplex method have to be of the form less than or equal to. How about the constraints if we have strict equations or bigger than or equal to form? This is the question we want to solve for today. So we say in some of the linear programming problems, we may encounter equations that do not have an obvious initial BF solution because there is no longer slack variables for us to use. For example, if we consider this linear programming problem with the constraints, if we want to start the simplex method as usual by first finding the augmented form by introducing slack variables, we can change all the inequalities to equations. However, we say if we want to set the initial BF solution as usual by setting the decision variables x1, x2 equal to 0, we can see this actually fails. Because even though we can find out the values of x3 and x4, the third constraint is an equation, 3x1 plus 2x2 equals 18. This does not fit if we want to set x1, x2 equal to 0. So simply by looking at this system of equations, it's very hard for us to find the initial BF solution. However, we say in order to start the simplex method, it is necessary for us to have an initial BF solution. So in order to solve such problems, we introduce an artificial problem that has the same optimal solution as the real one by making two modifications as we will introduce. First, we say we apply the artificial variable technique by introducing non-negative artificial variable into the equation, just as if it were a slack variable. And then second, since we introduced the artificial variable, it should not exist at the beginning. In order to eliminate the effect of this artificial variable, we assign an overwhelming penalty for having xi bigger than 0 by changing the objective function from maximizing z equals ax1 plus bx2 to maximizing z equals ax1 plus bx2 minus mxxi, where xi is our artificial variable. And this symbolitically represents a very huge positive number, so that in order to obtain the maximum value of z, we force xi to be 0. For example, in our original setup of our linear programming problem, we used to have 3x1 plus 2x2 equals 18, but this won't give us an initial BF solution. So we add an artificial variable x5 just as it were a slack variable. And then, since this should not exist at the beginning, we add a penalty to our objective function minus mx5, so that during our future process, to find out the optimal solution, we have to force this variable to take value 0, and then it won't affect our optimal solution. Okay, so now in order to start our simplex method, we say, well, we can make decision variables x1, x2 being 0, and then we have enough slack variables x3, x4, x5 as our basic variables. However, we still have one more step before we start the simplex method, because as we saw from the earlier examples, in the simplex method, we always want our objective function z to be expressed in our non-basic variables only. Here we have non-basic variables x1, x2, but x5 is the artificial variable we introduced. This performs the role of a basic variable. It should not exist in our objective function. But that's not a problem, because we have a relation between x5 and x1, x2. So we can simply do a substitution. X5 equals 18 minus 3x1 minus 2x2. And then substitute it into our objective function so that our objective function is expressed in terms of x1 and x2 only. So after we put our objective function in the standard form, it only contains the decision variables x1 and x2. And after moving all the variables to one side and keep the constant term to the right side, we can set up our simplex tabular and then apply the simplex method. So we first set up the simplex tabular, and then from the tabular, we start the optimality analysis. For the optimality test, we first check in equation 0, are there any negative coefficients? We have 2 negative coefficients. And since we say m is a very huge number, so m actually dominates this difference. So negative 3m minus 3 is actually a bigger coefficient in absolute value. So this is our pivot column. After finding the pivot column, we do the minimum ratio test and find out that this is the corresponding row, and then we find out the corresponding leaving variable, the corresponding entering variable, and then play the same trick as usual by doing Gaussian elimination, make that column unit. So we'll omit the detailed calculation, and interested audience can check the calculation and the tabular themselves. So we do the iteration first and find out a new BF solution and a new simplex tabular. And in the tabular, again, we see that there is a negative coefficient in equation 0. So this negative coefficient gives us another pivot column, and again, do the minimum ratio test. We find out the leaving basic variable. So do the Gaussian elimination, make that column unit, and repeat the same procedure. And then we find in the new tabular, again, we have a negative coefficient in the first in equation 0. And then repeat the same procedure using the minimum ratio test, find out the leaving basic variable, and make that column unit. And at this step, we can see that now all the coefficients in equation 0 are non-negative. So this passed the optimality test, and then this gives us actually the optimal solution. So at this point, we can read the values of z, the objective function, and the values of our basic variables, x1, x3, x2, from the right side. And then we find out at this point, we have the optimal solution, and then the value of our objective function. So this is the basic idea of the Big M method. As we expected, we say here x5 and x4 are the variables we introduced, and then they take the values 0. Okay, so next we talk about, so this Big M method help us to solve the problem when we have equations and it's hard for us to find out the initial BF solution to start a simplex method. Next, we talk about how to deal with constraints in the bigger than or equal to form. So if we have a bigger than or equal to form for the constraint, we can do as usual by introducing a slack variable, but of course our slack variable is non-negative, so we can do minus for the slack variable to make it an equation. For example, if we have this inequality 0.6x1 plus 0.4x2 bigger than or equal to 6, then by introducing a slack variable x3, we can make it as 0.6x1 plus 0.4x2 minus x3, where x3 is non-negative, equals 6. And then, however, again, if x1, x2 are decision variables, setting them equal to 0 will not give us an initial BF solution, because then we'll have x3 equals negative 6. That fails the non-negativity constraint. So in this case, if we have the bigger than or equal to constraints, by setting the decision variables to 0, we may still not able to find an initial BF solution. But as we saw earlier, it is required to have an initial BF solution to start our simplex method. The idea to solve such problems is similarly as before. After we introduce the slack variables, we have an equation. And then in the past, we say to deal with equations, all we need to do is to introduce an artificial variable and give a penalty to our objective function for having that artificial variable. So we do the same thing here. After we have introduced the slack variable, we obtain the equation. Since the equation won't give us an initial BF solution, we add an extra artificial variable to that equation and write the constraint as, same as before with the slack variable, and then add an artificial variable x6 equal to 6. And then if we have the objective function, remember this is the artificial variable, so we need to give a penalty to our objective function. So let's look at an example. If we want to minimize this objective function of 0.4x1 plus 0.5x2 with all these constraints, we say in order to start the simplex method, we first find its augmented form by changing all the inequalities to equations. So we add a slack variable to the first inequality and then add another slack variable to the third inequality. We have plus x3 and minus x5 for each because we want all the variables to be non-negative. However, at this point, we say even if we set the decision variables to be zeros, we still cannot find the initial obvious BF solution because of the equation constraint, equation 2, and then the constraint 3, which is bigger than or equal to. So in this case, we have two equations with problems in the equation. In this case, we say, as before, since we have problems for the equations, we introduce artificial variables for each equation and then change our constraint 2, which was an equation, as same as before, 0.5x1 plus 0.5x2 plus an artificial variable x4 equals 6. And then with this equation, again, we introduce an artificial variable plus x6 equals 6. And then, since x4, x6 artificial variables, they should not exist at the beginning, we add some penalty to our objective function. Note that in this case, in our objective function, we actually have plus m instead of minus, because in our objective function, we want to find out the minimum z of this form. So in this case, we want to add a positive n as large as possible to give a penalty for our objective function and forces our artificial variables x4 and x6 to be 0 eventually. So this is the idea of how to first, to set up the simplex method, if we have equations or constraints of the bigger than or equal to form that prevent us from finding an easy or obvious initial BF solution, what we do? We introduce the artificial variables and then give some penalty to our objective function to eliminate the effect of the artificial variables, and then start the simplex method as before. And in this case, since we have the minimization problem, in order to start the simplex method in its standard form, of course, we change the objective function to maximizing negative z, and then with all these constraints, with all the basic variables and non-basic variables, we can list out the simplex tabular and then do the use the simplex method to find an optimal solution. Okay, so the detailed calculations will be omitted here.